Thank you for invitation. Second time I visited this Congress, and I can see that it's developing. So my talk, it's about two directions in analysis. First one is property of subsystems of orthogonal systems, and second is the estimate of Kolmogorov widths. Both topics now became important for application, and the result, applied result I'll speak about, it's exactly at the intersection of both areas. Let me start with to present some result in direction 1 and 2, because I'm not sure that it's very much known here. And the application, it's about so-called phi widths or restricted widths. I'll give the definition later. And I already told you that it's exactly on the intersection of this topic. So first direction, we have a arbitrary orthonormal system, say on 0, 1, and the result by Marcinkiewicz and Menshov in 1936, that we can subtract a convergence system from the system phi, because it's not always the case. There are some systems which doesn't have this property, but we can find a subsystem with such a supplementary property. In modern setting, it's interesting to study how dense this subsystem is. And I should say that there is no technique for solving this problem. The best known result for arbitrary system is the exponential estimate, but we can expect that k power 1 plus epsilon also is good, but no proof. And second result by Banach. So if we have p equals bigger than 2, then we can subtract so-called SP system. So the system which generates subspace on which LP and L2 norm are equivalent. Here, as showed many years ago my PhD student Agaev, generally speaking, in such a setting, we cannot guarantee any density of subtracted subsystem. Next result, it's Marcinkiewicz result. So if we have orthonormal system with bounded from below L1 norm, so it's not localized function, not localized on the small set, for example, then we can find so-called Banach subsystem. It's exactly the system for which L1 and L2 norm are equivalent. And for example, it's unknown how dense such subsystem of trigonometric system could be. There is general result, but the same Agaev, but all very weak. So MK worse than exponential. Next, it's a result. It's mine. It's about so-called Sidon subsystem. Here, it's exactly the condition of Sidon subsystem. It means that the uniform norm of any polynomial is just a sum of absolute value of coefficients. It makes sense for bounded orthonormal system. And what was proved that from n functions, we can always find log n subsystem, log n exponent such that the this condition holds. It's sharp. It was known long time before. If you consider trigonometric system, it's always, we cannot find Sidon subsystem more dense than log n. Next result is a famous result by Bourgain. Here we consider the same SP condition, but under stronger condition on the system. Not arbitrarily bounded in LP, but uniformly bounded. And then there exists subset of such size and it's sharp. Then LP norm is bounded by L2 norm, so they're equivalent. This result is already has some applied value. And this, now I go to the second direction. It's Kolmogorov-Witz. It's what is it? For fixed n, the nth Kolmogorov-Witz is the best approximation of set K by n-dimensional linear subspace. It's not Kolmogorov. It's interesting. He considered not only Banach normed space, but linear metric space. And nowadays, Hamming metric, it's very important application of this notion. So we are looking for a best n-dimensional subspace. And this concept play fundamental role not only in approximation theory, but also in discrete mathematics, where they study it under another names. For example, let Mn is a set of all Nn matrices with real elements. The well-known in discrete mathematics definition is the approximate epsilon rank, simply epsilon rank. What is it? We try to make rank of matrix smaller, just changing a little bit elements. So we consider this minimum of over all matrices B such that element of A and B are close enough, less than epsilon. And there are many problems about this quantity, but the point is that if we consider the set of rows of the matrix and take the convex combination of it, then this number is exactly connected with width of the set of all of union of rows, all the same columns. So it's exactly a problem about width. And another quantity that play important role in discrete mathematics is matrix rigidity. This is definition. Now we are looking for a minimum possible number of elements to change in order to make rank at most R. There is a famous problem in this area. Give explicit example, rigid matrix. And it's unknown. It's connected with the also famous problem in width theorem to present explicit subspace, which good approximation, for example, of a Euclidean ball in uniform matrix. I'll speak about it a little bit later. the first problem about width estimate was considered by Kolmogorov itself, and the first group of problem, it's about Sobolev classes of widths. This is, the solution was obtained a long time ago by myself, and the result is the following. But what is interesting, that even for ordinary smoothness, it was one case not fully investigated. So exactly this case. So W11 in the matrix LQ, Q bigger than 2. What is the problem? We have a set of functions, here 0, here 1, all class of monotone functions, and we would like to approximate by n-dimensional subspace, best way. And it was unknown for many years, and this year Malichin from Steklov Institute got this theorem. So the best approximation, the Kolmogorov width, is of order log n divided by square root of n. This problem of estimating of Kolmogorov width for Sobolev classes normally are closely connected with the finite dimensional problem, geometrical problem of widths of ball of the space LP in the norm LQ. But in the case W11, it's not the case. The following equivalence holds. So what we need to estimate, it's a finite dimensional width of the set of these rows. Here it's 1, 1, 1, and so on. Here it's 0, and here always 1. And such n vectors, it's Q octahedron, and it was the result of Malichin to estimate this finite dimensional widths. As about previous problem, number 2, it's very well studied since 70s, and everything is known except one case, P equal 1, Q equal infinity. It's not the main interest, but because the main problem here is P equal 2 and Q equal infinity. This width has a lot of application in different domains, but this problem is also for P equal 1, Q infinity is also interesting. And it's exactly the problem of epsilon rank of identity metrics. And in this regard, another interesting result of Malichin this year. So this n times n unit matrix, 1, and here 0, could be approximated with good error, say 1/3, by the subspace of the logarithmical dimension. It's well-known classical result, but the result, what he proves that in such a case, always a lot of such a matrix A approximating identity has a lot of big elements. Here is his theorem. And very interesting problem. It's about width of this set of vectors in L infinity norm. We tried hard, but there are many proofs, but what is known only is the following. We cannot uniformly approximate this matrix by matrix of rank log n cube, and cannot approximate well of matrix of rank log n square. It's a very interesting problem, but mostly for discrete mathematics. Now I came to the intersection of both this direction. And what is the phi width? In 1974, Ismagilov introduced the concept of trigonometric width or restricted width. What is the difference with usual width? We fix the system and looking only for subspaces generated by subset of this system. So subsystem. And he start trigonometric case. And he got interesting result why this area start to develop. First of all, it's classical result by Bernstein that the function absolute value cannot be the best approximation by ordinary trigonometric polynomial in uniform norm is n minus 1. But if we choose harmonics smart way, we can approximate better, much better. And it's why the whole topic starts. It's equivalent because this function, extreme function of this class, so he got this estimate, and then it was improved till n minus 3 over 2, but more generally, if we fix this orthonormal system or just arbitrary system, we can introduce this phi width or restricted width. The restriction means that we consider only such a subspace. Only such a subspace. And the following theorem was proved by 4 French mathematicians. In fact, not all of them are French, but it's an important result, and I will use it in application. What about this result? If we have uniformly bounded orthonormal system with n elements, we can split the system into 2 parts, such that for all coefficients, for all polynomials with respect to one part, and with respect to the second part, L1 and L2 norm are almost equivalent. You see, if we consider general subspace, it was my result of 70 that we can get it without any log. But if we fix, say, for example, trigonometric system, we cannot remove the square root of logarithm. It was shown by Bourgain, and the only problem is about this iterated logarithm, but it's not very important number here. And in fact, it's from one side, it's result about Banach system. So L1 and L2 norm are almost equivalent, but by duality, it's a result about phi widths, because it's equivalent to the following estimate. So we try to approximate big one Euclidean ball uniformly by this half-dimensional, almost half-dimensional subspace. And we can do it with such error. So it's 1 divided by square root of n, it's very good number. And this is a little bit worse than for arbitrary subspace, but the point is that we can choose our subspace in each as a subsystem of arbitrary system. Why it's the same here? It's a simple argument. I don't want to repeat it. It's clear. By the way, from this theorem for author, it's easy to prove that trigonometric width of Sobolev class has this estimate. So, as I wrote, the general Kolmogorov width, we don't need this extra logarithmic term. It's a sharp result. It's n minus r. But if we lose a little bit, we can select our subspace as a set of classical harmonics. But the big problem to find effective way to do it, because all methods here are random. So we need to select harmonics by a random procedure. And fortunately, in many cases, it's not very bad. Some devices works very well with such random selection. Now I'd like to present two application of this results. First one is a recent paper by Yosevich, myself, Limonova, and my elites, Russian-American team. And the title is here. And the result is the following. We have a arbitrary orthonormal system, orthonormal basis, and if we normalize it in Cn, that of course the uniformly boundedness condition should be rewritten in as here. So renormalize it because in L2 the norm 1, so it's natural renormalization. By signal we mean just a vector. And support of f is a set of non-zero coordinate of signal of vector. By fn hat, we denote the Fourier coefficient with respect to this basis. Our main interest will be connected with case when phi is trigonometric or Walsh system. Okay, and what we are looking for, what kind of problem we would like to solve. Let me first explain. What we should guarantee that any signal f, such that it's sparse enough, so the cardinality of the set J such that Fj equals 0 is much less than n. If we have such a signal and we transmit it, and we lose, during the transmission, we lose almost all coefficients, Fourier coefficients. But still we would like to reconstruct exactly our signal. Is it clear what I'd like to say? So the goal, it's very natural. So we transmit sparse signal, we lose most of the information, but still we reconstruct this signal. And using these theorems, it's possible. So let me give the definition. The set is lambda is a stable recovery spectrum with parameter S for the orthonormal basis phi. Yet if each signal with small sparse enough can be uniquely recovered from the value f hat n, where n belongs to lambda. And using in this class of problems, the standard way of reconstruction, L1 minimization algorithm, like in compressed sensing. And the result is I don't know this set of stable recovery spectra, but SRF phi S, and introduce this number. It's a little bit less than n. And repeating our argument from the paper with Temlяков, we have a following theorem. Almost, I can reformulate it in a less formal way. So almost all if our laws are random, that with probability almost 1, we always can reconstruct our signal if it's sparse enough, and sparsity is not so big. Instead of n, we have to have a sparsity n divided by this logarithm n. So it's big number of non-zero coefficients, a lot of possibility of transmission, but we need a little bit to keep some sparsity. And in such a condition, we, with very high probability, can reconstruct our signal exactly. And second result is of different nature. I start with my PhD student Romsky. It was proved the following. It's not about phi widths. Phi widths will be later, but now we consider the group of orthogonal matrices, and for all orthogonal matrices, except of exponentially small subset of group, and for any x from Euclidean ball, a greedy algorithm, there is a greedy algorithm such that he decomposed the vector x into two vectors with extremely small uniform norm, but in different bases. What is a greedy algorithm? It's very easy. The greedy algorithm always needs some dictionary. So I take a unit cube and I consider the set of vertices of unit cube in Rn, and I unify with rotated set. V, it's not very good. let's denote the set of vertices En, V of E infinity n. So, and what is a greedy algorithm? If I have vector x, and I have this dictionary, I just, the first step, I find the closest line from this set of direction and from this set of direction. So, and it's easy to see that it's exactly the minimal, the line which minimizes the uniform, the L1 norm. L1 and maximize to number and norma V of X L1n. And this algorithm works very well because it was a theorem of mine, very old one, that for all metrics except very exponentially small subset, we can guarantee that for arbitrary x, this maximum is big. So why this greedy algorithm works very well? And we obtain the result that could be, some people use in federated learning and in the quantization of big vectors in large language models. But such a result has some disadvantage, because we need to select our matrix V. Size this matrix is n is huge, and we need to keep n square element of this matrix. Here I denote it by Q. And also the multiplication of vector by matrix is n square operation on each step of algorithm. And then naturally, question arises of accelerating this algorithm and reducing the memory required. And in this direction, the result about 5 widths are very good. So, especially good if we can compute multiplication fast way. So let phi will be orthonormal basis in Rn now. Epsilon is this vector of choice of signs, and we consider the following. We consider the following easy operator. It's just Fourier operator in this discrete case, and it's inverse. So, and T epsilon is multiplier operator. So what we do, we take a function or polynomial or function, discrete function, we decompose into Fourier series, then multiply by plus minus 1, and then take inverse. It's our main object. And I should say that when phi is trigonometric system, discrete trigonometric system, or discrete or Walsh system, this operator computed using fast Fourier transform, it's instead of n square by n log n operation, it's a huge, huge impact. And using theorem 8 about general orthonormal system, we can show the following result. It's not yet published. This year will be published in mathematical notes. For any orthonormal basis and for most set epsilon, the corresponding greedy algorithm works very well. I should precise what kind of greedy algorithm I consider. It's exactly the same as I tried to describe earlier, but just I take vertices of initial cube and I take the set of 2 power n vertices of rotated cube. And it will be 2 times 2 power n vertices. It's my dictionary, and our standard greedy algorithm in Hilbert space works very well if V is not arbitrary, but special kind of basis. And what we can get, we construct such a decomposition of arbitrary vector V of arbitrary vector X into sum of 2 vectors. Both of them have very small coordinates. Looks instead of 1, because it's normalized in L2, so the coordinate of X of order 1. But here we have 1 divided by square root of n in 2 different bases. And the order is a little bit worse than our result with Romsky, but in fact, it's when you take experiment, it works much better. And the advantage of this algorithm, then, as I already said, that it's very fast. Instead of in square, we need n log n on each step. And I'd like to say that now there is very fast developing direction is federated learning. And they use my previous result also, but I hope that this kind of algorithm could be most successful. So I think it's all. Thank you.